Okay, welcome to the beginning of the very last unit that we will talk about in AP Physics. This unit is on gravitation, and I love having this unit last, not only because the topic is very interesting to me, but also because it's a good wrap-up of a lot of other stuff we've done. Just kind of like rotation, it does incorporate forces, energy, momentum, stuff like that. And you'll see that if you are familiar with the few basic equations that you need to know, you can really derive and determine some very interesting things that happen when we talk about gravity in a larger sense, not just the force of gravity here on Earth, but the force of gravity between very, very big objects out in space. So as we know, gravity is a force that acts between objects that have mass, and it is always attractive. So we have that gravity is an attractive force between objects with mass. Okay, the objects have to have mass in order for them to interact via the force of gravity. If we just want the local gravitational force here on Earth, or a location with a known g, a known acceleration due to gravity, finding the force of gravity is very easy. It's simply Fg equals mg. And on Earth, we know that g is approximately equal to 9.81 meters per second squared. And in AP Physics, we say the extra detail doesn't really matter. We don't care about the exact calculation, we care about the concept, so we're just going to use 10. And this is changes in other locations. You go farther away from the Earth, you go up in any direction from the Earth's surface, g will decrease once you get far enough as you go up. It doesn't noticeably decrease until you're very far away, but it does decrease. Okay, so it changes in other locations. On other planets or moons or asteroids or wherever, g would be different. You'd have to figure it out for that location. We also know that the Newton's universal law of gravitation is Fg equals g m1 m2 over r squared. Sometimes in this class, and I can't remember exactly what the reference tables say, you might see it as g little m big M over r squared, where little m is the smaller mass, big M is the bigger mass. In this equation, either way, it's that there's two different masses. Big G is the universal gravitational constant, which is 6.67 times 10 to the negative 11th newtons times kilograms squared over meters squared. The reference tables might give different units, different but equivalent units. I can't really remember what they say. And r, as we know, is the distance between the centers of mass of the object, not the surfaces of the object, the center of mass of the object. So let's start out with the really basic stuff. What would the weight of a 90 kilogram astronaut be on the moon? The lunar mass is 7.35 times 10 to the 22nd kilograms, and its radius is 1.737 times 10 to the 6th meters. So you have to know a couple things to do this. You have to know that weight just means force of gravity. Now we can't use this equation because we don't know g for the moon. We don't know the acceleration due to gravity on the moon. This is a pretty standard Regents question. We would use this, Fg equals m1 m2 over r squared. G is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. The mass of the astronaut, the m1, or little m if you like, is 90 kilograms. The mass of the moon is 7.35 times 10 to the 22nd kilograms. And the radius, remember to square it, is 1.737 times 10 to the 6 meters. And that's the distance between the objects because the astronaut is standing on the surface of the moon. So the distance between the objects is not zero. It's not the distance between their centers. It's the distance, it's not the distance between the surface of the moon and the astronaut. It's the distance between the center of the moon, the center of mass, and the astronaut. So that would be the radius of the moon. So we calculate this, and like I said, this is a very standard Regents level question. That's why we're starting off with this. 6.67 times 10 to the negative 11th times 90 times 7.35 EE22 divided by, I'm put in parentheses, 1.737 E6, square that, divide, and we end up with approximately the force of gravity on this astronaut is 146 newtons. Now, if we compare that to the astronaut's approximate mass, or excuse me, weight on Earth we estimate by multiplying the mass by approximately 10, so that would be 900. This is about 1/6 of the Earth's, am I doing that math right? Yeah, this is about 1/6 of his weight on the Earth. So we would say that gravity, broadly speaking, on the moon is about 1/6 the size. Now let's do a little bit trickier question. If instead the astronaut was orbiting a distance of 1 lunar radius away from the surface, what would their weight be? So here's how we picture this. Here's the moon. Here's the radius of the moon. Now first, the astronaut was standing here, but we're saying what if instead he is orbiting? He's going around the moon, he's in a spaceship, and he is that much farther out. He's 1 extra radius out from the center of the moon. Well, he's now 2r. The distance between the moon and him is, the center of the moon and him is double what it used to be. It used to be just r when he was on the surface. Now it's 2r. Does that make sense? So, we could just double the radius here and then plug everything back into the equation. Or we can reason about it a little differently without having to do all that math. I'm going to write down FG prime. Prime just denoting that, hey, something's different here. G, M1, M2. None of those things change. G is a constant. We haven't changed the mass of the astronaut or the moon. What we have changed, though, is the distance away from the centers of the objects. The distance separating the centers of the objects. That has changed, so I'm going to put that as R prime. And we know that R prime, this new distance, is really 2 times the original. So here's what I'm going to do. GM1, M2 over 2R squared. And it's important that you put these parentheses because you have to realize that order of operations matters. We know that in order of operations, exponents come before multiplication. So it's crucial, but parentheses come before exponents. So it's crucial that we put parentheses around the 2R because we want the distance to be multiplied by 2 before we put it into the equation. Okay? We're not squaring the old distance and then multiplying by 2. That will not give you the same answer. That will give you an answer that is off by a certain factor. Okay? So when we put this into parentheses, we're saying, hey, the new radius is twice as big as it was originally. Now we're squaring it. So GM1, M2 over 4R squared. Take a look here. GM1, M2 over R squared was just my original force of gravity. The only thing that's different is I added an extra factor of 2 to the radius, to the distance between the centers of the objects, and because they had to get squared, look what popped out. There was a 4. So now I see that the force of gravity is 1/4 the size of the original. And if I take 1/4 of 146 newtons, I see that what I get is 36.5 newtons. Now you can go and verify for yourself that this works out to the exact same thing that you would have gotten had you just doubled this number and plugged everything in. Okay? This, to me, is a little bit of a quicker way to do this problem. Okay? It involves less risk because you don't have to make all the calculations. What if you type something in your calculator wrong? Okay? As long as you're set with your algebra and the process of how this works, this is a quicker way to do this. Let's move on. Let's do a couple more of these. A certain planet has a mass of m and a radius of r. If an object of mass m from that planet is taken and placed on a planet of mass 2m and radius 3r, how much larger is its weight on this new planet than on its original planet? So we're comparing the weight of an object on 2 different planets. So I'm going to have P1 and I'm going to have P2. On planet 1, we are told that, let's see, so we know the universal gravitational constant is going to be involved. We are told that there is an object of mass little m on a planet of mass big M. And that would be over, since it's on the surface, the distance between the center of the planet and the object that's on the surface is just r. So originally, the force of gravity on this object on this first planet is g little m big M over r squared. We're taking that object and putting it on another planet. This planet is a little bit different. The mass of the object is still the same. The gravitational constant, the universal gravitational constant is still the same, but the mass of the planet it's moved to is bigger. It's now 2m. And the radius of that planet is bigger. It is 3r squared. Now I guess I could have had a step where I put in like m prime, big M prime, and r1 and r prime squared, but I'm just skipping those steps. I think you can follow along. So the goal here is for me to be able to bring these constants out to the front, okay, so I can look and see by what factor this whole thing has changed. You know that multiplication, the order doesn't matter, so the fact that the 2 is in here, gm times 2m, that doesn't really matter. I can bring that 2 out to the front, and I can say that this is 2g little m big M over, well, this is 3r. If I square that whole thing, what does that become? Just like squaring 2r here became 4r squared, squaring 3r becomes 9r squared. And once again, look what I have here. G little m big M over r squared is just the same as the force of gravity from the first planet. So I see that this can be replaced by Fg, and the force of gravity on this second planet is 2/9 the size of the force of gravity on the first planet. You might say, well, wait, the mass was bigger. Shouldn't that attract it more? That's true, but the radius was bigger by a factor of 3. And because the radius is squared in this equation, the distance between the centers of the objects is squared in this equation, that factor ends up meaning more. So this is much more important that the distance between the objects triples than just the mass doubling. Okay, it's much more important. So we have a smaller force of gravity on this planet, basically because that planet is much bigger, okay, in terms of its size. The object is farther away from the center of gravity. Now here's a much trickier one. This is more on level of like an AP question. Not that you get a ton of these, but you do see them every once in a while. How does the weight of the object compare on a third planet that is twice as dense as the original within a radius of r over 3? And in order to do this, we need to talk about density. Now, density is a really simple equation. You learned it back in 6th or 5th grade, somewhere around there. Let's start by talking about planet 1. The original density of this planet, density, if you remember, is just mass divided by volume. And we know that in physics, we don't use d for density. We actually use the symbol rho. You might remember rho from Regents physics. It's kind of like a rounded P with a tail that kind of curves in like that. So rho equals the mass divided by capital V, the volume. I'm going to rearrange this to solve for the mass of the planet, okay? And it'll be clear why I'm doing that in a little bit. The mass of the planet would be equal to rho times the volume of the planet. And let's think about what we know about the volume of the planet. The volume of a planet's a sphere, so the volume should be the volume of a sphere. The equation for the volume of a sphere is 4/3 pi r cubed. So I'm going to write it like this. The mass of this planet, the first original planet, is equal to 4/3 times pi times r cubed multiplied by the density. Okay? Let's go over to planet 3. We don't know anything about the mass of planet 3. However, we do know something about the density of planet 3. And because we know that density and volume help us to determine mass, we can figure out the mass that way. So this one requires some prep work. The mass of planet 2, so I'm just going to call it m double prime, because we already had m prime, or we would have had m prime up there. The density is twice as big, so I'm going to do, eventually I'm going to do 2 times rho down here. The radius is only 1/3 the size, so I'm going to say that the mass of planet 2 is 4/3 pi r over 3 cubed. I'm going to put all that, just to note that this is all the volume, multiplied by 2 rho. Let's do the math and figure out what this will be. If I cube r over 3, I should get r to the third times 3 times 3 times 3 or over 3 times 3 times 3 is 27. So this becomes out front 4/3 times 1 over 27 times pi times r to the third. All I've done is I've split up the 1/27th and the r to the third. And this is still 2 rho. Okay, so this is getting real complicated now. Let's see here. What can we do? The factors that are really different here are the 2 rho and this 1/27th. I'm going to bring those to the absolute front. So I have 2 over 27. I'm going to leave the other ones inside. Because if I leave the other ones inside, what you'll notice, if I have 4/3 pi r cubed times a rho, that's exactly what I had here. What this shows me is that the mass of the second planet, if the density is twice as much, but the radius is only 1/3 as much, the mass of the second planet must be, after all this algebra, 2/27ths of the mass of the original. The reason this is important is now I'm finally able to predict what the weight, the force of gravity, on that other planet is. Because now I know the mass. I know that g and little m aren't changing. I know the mass is 2/27ths the original. And I know the radius is 1/3 the original size. Okay? So, here's what I'm going to do. This becomes g, here's what I'm going to do. Let's see here. If I have 2 over 27, that whole thing can get moved to the front. So I have 2 over 27 times g, m, big M, over r squared over 1/9. If I have a fraction in the denominator, I can bring the denominator of that fraction up to the top. That gives me 2 times 9 over 27 times g little m big M over r squared. This is simply the original force. 2 times 9 is 18 over 27. This whole thing, we just did all that work to show that the force of gravity on this third planet is 2/3 the size of the force of gravity on the original planet. There. I'll be right back.